because physicists had observation they could not understand. For instance, the light emitted by matter when excited, they could not describe the quantitative properties of this light by using the physics that they knew. Physics was quite developed at the end of the 19th century. Classical mechanics, Newton, motion of planets, etc. has been well established. Electromagnetism had been well established. Maxwell in 1865 has written a series of equations that we still use for describing electromagnetic fields, etc. The interaction between charged particles and matter was understood. So normally people have all the tools to describe matter, the way in which matter emits light, the way in which it absorbs light. But when they were trying to make sense of what they observed, it did not work. It did not work at all. I will not go into the details of the properties of radiation, but I want just to mention one point that everybody should understand. They knew that matter was made of charges, positive charges and negative charges, with as much positive as negative charges, so that matter at the end is neutral. And they knew that charges with opposite sign attract each other. Positive charge attract negative charge and vice versa. And so if you think that you have positive and negative charge in a piece of matter like that, positive and negative charge should attract each other and matter should collapse. Why is it that it did not collapse? It took the hypothesis of extraordinary behavior, impossible to understand in a classical way of thinking, to understand why matter does not collapse. And that new concept is called wave-particle duality. Wave-particle duality was first understood by Einstein about light. Einstein understood that light, which is a wave, according to what had been established clearly at the beginning of the 19th century by Thomas Young in England, Augustin Fresnel in France. They have established the fact that light is a wave. They did not know the nature of the wave, but after Maxwell's equation, it was clear that the wave was electromagnetic. So by the end of the 19th century, there was no doubt light is a wave and all optical phenomena can be described assuming that light is a wave. But Einstein spotted a few phenomena where he said these phenomena, you cannot understand them by assuming that light is a wave. You must assume that light is made of grains of energy, like small particles, but particles going at the velocity of light, because we are talking of light. And this particle, Einstein called it Lichtquanten in German, which means quantum of light. Nowadays, we call them photons. And so Einstein understood that some phenomena will be understandable only if you introduce this idea that when you have a beam of light, in fact it's a beam of small particles called photons. But on the other hand, he knew his physics. He was a good student. He had studied classical optics. And he knew that there are many phenomena in which you must describe light as a wave. What can you do? Well, Einstein was not a man to hesitate. He would be ready to change all our concepts. In 1909, we have to accept that the wave-like behavior and the particle-like behavior of light both exist although they look to us contradictory. Yes, they are contradictory, but anyway, you have to accept too. Okay. 14 years later, my compatriot, Louis de Broglie, in 1923, made the reserve reasoning. Einstein, I told us, we think that light is a wave, but it is also a particle. What Louis de Broglie did is say, we think that electrons are particles. Yes, they are particles. When an electron bumps into an atom, the atom recoils, etc. There were observations of that kind. But we must also consider them as a wave. And he wrote a formula associating a wavelength, which is a characteristic of a wave, as a function of the velocity of the electron. And almost immediately, it allowed physicists to understand some observations. First, the idea that the energy levels of atoms are quantized. Bohr had made an hypothesis. Nobody really understood where this hypothesis came from, but it turned out that by making his hypothesis, Bohr could describe the property of light emitted by atoms, and in particular the atom of hydrogen, which was one of the problems that physicists did not understand before the invention of quantum mechanics. So Bohr made an hypothesis that people did not really understand. And then, when de Broglie comes with his assumption that an electron is a wave, immediately the quantization condition of Bohr became clear. The idea is the following. The model of the atom, invented by Rutherford, which is a good model, it has to be refined, but it is a good model, good starting point, is the fact that you have a nucleus which is positive, and you have electrons turning around. And it's just like satellites around the Earth, or just like planets around the Sun. But according to Bohr quantization rule, only some orbits are permitted, and it is by jumping from one orbit to another orbit that the atom absorbs or emits light. But why is this orbit? Well, with de Broglie hypothesis of wave-particle duality, you can immediately understand. If you think that the electron propagating on its orbit is a wave, after one full term, the wave must return in phase with the waves that you had before. In other words, the number of wavelengths that you have in the length of the trajectory must be an integer number. Otherwise, you are oscillating like that, and after a term you are oscillating differently, doesn't work. It's not stable. So this condition of stability of the wave after one term was just what you needed to understand Bohr condition of quantization. This was 1923. When you have a wave, all physicists look for the wave equation, an equation of which the wave is a solution. And a physicist, mature physicist, a mentor, told the young Schrödinger, you are gifted. If there is really a wave, like this Frenchman says, there should be a wave equation. Look for the wave equation. Find the wave equation. And this is what Schrödinger did. Schrödinger found the wave equation of which the de Broglie waves were solutions. And then it was the Schrödinger equation. And once you have the Schrödinger equation, you have all modern quantum physics. It has been slightly refined by Dirac, who published in 1930 beautiful mathematical formalism, of which Schrödinger equation is only one version of that formalism. But so I mean that in 1925, everything was set. We had the equation to understand why matter is stable, why the electron remains at a distance from the nucleus and matter does not collide. We had the equation to understand the chemical bond between atoms. For instance, in the hydrogen molecule, you have two hydrogen atoms. Why are they fixed to each other? Why in a piece of carbon do the carbon atoms are maintained close to each other? Schrödinger equation allows you to understand that. And after the work of Dirac, you can also describe how light is emitted or absorbed by matter. This was 1925. And so I am speaking of the first quantum revolution, and what we have seen already in this first quantum revolution is a conceptual revolution, wave-particle duality. And now we have a scientific revolution. Now we have the tool to understand why matter is stable, how matter emits light or absorbs light, etc. So it's a scientific revolution. Now there is a third point of view in a revolution. The third one is application. Do we have application? Yes, but it took a long time. First real application of quantum mechanics, transistor, invented in 1947, 22 years after the establishment of the Schrödinger equation, more than 40 years after the first ideas about quantum mechanics, 4 decades, and 22 years after Schrödinger equation. And you know how they discovered the transistor? Not by chance. The people who discovered the transistor were the best physicists of that time, trying to use Schrödinger equation to describe accurately the motion of the electron in matter. Okay. And they succeeded. And then they began to apply this idea to some strange materials called semiconductors. And they got an idea. If I would have a semiconductor positively doped and a semiconductor negative doped, maybe something interesting would happen. And so they asked the engineer, do we have such materials? And the engineer say no. And so the physicists say, work hard. And so engineers began to purify the materials. And after purifying, injecting right the exact amount of impurities they needed. And eventually they could build the first transistor, which is at the root of all modern electronics. You are going to tell me, come on, integrated circuits are not transistors. Yes, they are transistors. A microprocessor is millions, billions of transistors on a chip. So once you have the transistor, you need another 2 decades to invent it, integrated circuits. And notice, all these things are not made by chance. It's people thinking out, using the law of quantum mechanics. And the proof is that at the end, not only they have a beautiful invention, and probably they make a lot of money with this, but they get a Nobel Prize. So it's really to say that this development of technology took time and took the best mind to do it. The other example of the first quantum revolution is the laser. Without laser, you have not information highway. You have not fast communication through optical fibers. If you take a normal lamp, a classical lamp, you try to inject the photon in the optical fiber, basically there is nothing. No power can pass the optical fiber. You need to have a laser. The laser was invented in 1960, 60. And the equations which are at the root of the working of a laser were invented, were discovered in 1916. 16. By whom? By whom? Einstein. This is why I write this book saying Einstein and the quantum revolutions. Einstein is at the root of so many things. The equation for absorption and emission of light by matter, the basic equation, have been written by Einstein in 1916, and the laser was invented in 1960. Think of it. So if there are venture capitalists here, know that your investment has to be very long term, okay? Now, second quantum revolution. They told me 20 something. Second quantum revolution. Second quantum revolution is based on entanglement. Entanglement is a property yet more counterintuitive than wave-particle duality. Wave-particle duality is about a single particle. What is strange is that you have both properties, but at least each property, I can describe it easily in our space. If I speak of a particle traveling in our space, well, everybody understands what it is. I can throw a ball, it has a trajectory, etc. If I describe a wave propagating in our space, you need to have done only a little bit of physics or mathematics to understand what is a wave which propagates and fills the space. What is strange is that you have the two properties for the same object. Sounds contradictory. It is contradictory, but it is a fact. But at least each concept, I can describe it in a rational way in our space. Entanglement, you cannot. I don't know any way of describing entanglement simply in our state, or I have to introduce a crazy concept which is non-locality, spooky action at a distance, Einstein would say. What is entanglement? It's the fact that if I have two particles, quantum particles, and they go far from each other, although they are far from each other, they can still, if you entangle them correctly, okay? Not all particles have this property. But if you do well your job, the two particles will remain entangled, which means strong correlation between measurement that you do here and measurement that you do there. I will elaborate a little bit on that. This is the experiment I did. Let us think of a photon. I can do a measurement of polarization on a photon. What is a measurement of polarization? If I set a beam of light on a polarizer, the light can go out either in one polarizer, you have two output channels. If light is polarized, that is to say vibrates, the electric field of light vibrates along the direction of the analysis of the polarizer, it will go out in the +1 channel. And if it is polarized perpendicular, it will go out in the -1 channel. And if it is polarized at an angle, a fraction of the beam will go up and a fraction of the beam will go down. But if you have a single photon, you are not going to get a fraction of the photon up and a fraction of photon down. A photon is a particle, cannot be split. And so if you set a photon, you will find the photon either up or down. When you find it up, you say, oh, my result was +1. When you find it down, you say, my result was -1. What can you do with that? Nothing. You must repeat the experiment many times, preparing the photon the same way. And if you repeat many times, you will look at the probability to get them up and to get them down. In the case of entangled photon like the one I was using, it looked totally random. Same probability to go up and to go down, and if you look at it, it looked totally random. Same thing on the other photon. Okay, on the other photon, I put a polarizer and I make a measurement, and whatever the orientation of the polarizer, it sometimes goes up, sometimes goes down. Looks totally random. Now I pronounce the word correlation. Where do I have correlation? If I have two entangled particles of the kind that I could produce in my laboratory, and if I take the same direction for the two polarizers, then something interesting will happen. People who are here will still see randomly up and down. This one will also see randomly up and down. But the people who are far here and observe both sides will observe a strange fact. When it is +1 here, it is +1 here, and when it is down here, it is down there. When it is -1 here, it is -1 there. There is a strong correlation. I have a random variable, I have a random variable, but these random variables are strongly correlated. Okay, how do I know? Well, first because I have done the experiment, but before doing the experiment, it is what was predicted by the mathematics of quantum mechanics. But Einstein said, look, if you have such a correlation, there is only one way, one reasonable way to understand this correlation, is to assume that from the beginning, the two particles has property that will determine that it will be, for instance, +1 +1. Next pair, there is a property saying that it will be -1 -1. So far, so good. Sounds very reasonable, very scientific. The kind of conclusion that you draw when you observe that twin brothers or twin sisters have same color of eyes and same property. You say, of course, they have the same chromosomes from the beginning, when they were created in the belly of their mother. It's the same set of chromosomes for the two, and so no surprise that they have same color of eyes. But Bohr did not like that at all. It was a big debate between Einstein and Bohr. Because by doing that, Einstein thought he could prove that you need to complete the mathematics of quantum mechanics. Because the mathematics of quantum mechanics describes all my pair with the same mathematical tool, the same quantum state, the same wave function. All the pairs are described the same. But Einstein said, no, some pairs from the beginning, you know they are going to be up, some pairs, you know they are going to be down. And Einstein, who liked to think that you must complete quantum mechanics, said, you see, you must introduce supplementary properties, you need to complete quantum mechanics. And Bohr said, no way, quantum mechanics as it is the end of the story, you cannot complete it. It was a long-lasting debate which was only about interpretation. There was no practical consequence. Einstein did not disagree on the result of the calculation. Bohr, of course, agreed on the result of the calculation. Until in 1964, a man raised his finger, it was John Bell. He said, excuse me, if I take the point of view of Einstein, I show that there are certain restrictions on the correlation you can obtain by assuming joint property, etc., so-called hidden variable. There are certain restrictions, and in some cases, the prediction of quantum mechanics go beyond this restriction. This restriction is known as Bell's inequality, and some prediction of quantum mechanics violate Bell's inequality, cannot be understood as explained by this supplementary parameter. And now you have a fantastic situation. It used to be a philosophical debate about interpretation of the world, but now it's more than a philosophical debate. You can settle the debate. Time's up. So I go away, or I'm finished. If you don't want me to finish, say it.
No.
Well, so it was possible to settle the debate by doing an experiment. The first person to do an experiment was John Clauser. He was one of the laureates of the 2022 Nobel Prize. Okay. What I did more than Clauser did the experiment with the two detectors and found correlation. What I did more is establishing non-locality. Non-locality is the fact that while the photons are propagating, I change the orientation of the polarizing. And I change on the other side. And the result that I found was depending on the orientation at the very last moment. And this establishes the fact that until the last moment, the result can be as well +1 as -1. Same on the other side. Until the last moment, it can be either +1 or -1. But when the measurement is done, you get +1, and then instantaneously you get +1 on the other side. That's quantum non-locality. Quantum non-locality is at the root of quantum communication technologies. These fantastic properties of entangled particles, the fact that you have more information in the entangled particle than in the sum of the information that you have here and the sum of the information that you have there. This capacity to store more information is at the root of quantum computers. So this discovery of entanglement is a conceptual revolution. Observing experimentally that entanglement is as extraordinary as predicted by the equation is a scientific revolution. Establishing quantum non-locality is a scientific revolution. And now we are in the process of the technological revolution with the development of quantum computers and the development of quantum communications. And entanglement was imagined in 1935 by Einstein and his colleague. Then John Bell added his stone to the story 30 years later, 29 years later, 24. We did experiments, Clauser in 72, my experiment was in 82, and now we are more than 40 years later, and we begin to have quantum technologies. So once again, it's a long way from basic concepts to application. Thank you for your attention.